Hi everyone, welcome to this episode of Keipert Labs. In today's episode we're going to discuss collision theory and equilibrium. So firstly we're going to review the concepts that we know about collision theory, some of the key ideas about how chemical reactions occur because of collisions between particles. We're going to remind ourselves of what we mean by activation energy, or EA. We're going to then look at reaction rates and a concept we call equilibrium position. So, we've talked about in the past this idea of collision theory as a way to explain why chemical reactions occur. That the idea that for a chemical reaction to occur, we need particles to collide. Things that are going to affect that is how often particles will collide, whether this collision has sufficient energy, and whether the particles collide with the correct molecular orientation. Are the molecules facing the right way when they interact with each other in order for bonds to break and new bonds to form. At sufficient energy of the kinetic energy of the particles so that when they collide that there is enough energy to overcome the bonds that exist and to break them and reconnect to make new ones. And so this energy that we need to put in, or the energy required for that reaction, we call the activation energy. So this is the amount of energy we need for that successful collision. Okay, so we give it the symbol of EA, so energy of activation. And so it represents the hill that we need to get over for the chemical reaction to occur. Okay, so the larger this energy value, the harder it is for that reaction to get started. But the idea is just like riding a bike to the top of the hill. Once you get to the top of the hill, then rolling down the other side is very easy. Okay, and so it's effectively a threshold for the reaction. That unless the collision, unless a given molecule has an energy greater than the activation energy, that collision won't be enough. Okay, so when we looked at the Maxwell-Boltzmann distribution of energies in the molecules, and recognizing the activation energy is this threshold, this point past which the collision will have enough energy for it to be successful. If it's less than that, then it won't be. They will just rebound off each other and go on their merry way. Okay, but so only molecules that have energy in this red zone here will have enough energy to react once they collide. Okay, now the thing is that we've just introduced this idea of equilibrium or reversible reactions. The idea that some chemical reactions where rather than just going from start to finish and that's it, that actually that we get two possible processes. We're going forwards and we're going backwards that can both occur. We reach this point of equilibrium, or this balance that occurs between these two processes where their rates are equal. But then it kind of begs the question of, right, well, if activation energy is the threshold we need to get over, then how are we able to actually go backwards? And so then what we have is that if we look at a diagram here, let's say, this is our reactant side and this is our product side. These are our energy of activation. This is the one to go from left to right, and this is the one to go from right to left. And so what we're saying for a reversible reaction, what happens is that there is a small difference between the activation energies of the forward and reverse reactions. That is, the energy content, the average enthalpy change is pretty small by comparison. That there's only a little gap. So it's actually not a huge hill to go backwards relative to going forwards. Whereas if the difference is much more magnified, then you can see that it would be a lot harder to go backwards. That's what the sort of thing we notice in combustion reactions, is that the amount of energy needed to go backwards is almost insurmountable. So, and it's not actually how that would work. And so when we have similar activation energies for the forward and reverse processes, that then our reversible reaction can be possible. Okay, and now we're going to think about, from collision theory, what we understand about rate of reaction, see how that we need to modify or incorporate this idea of equilibrium. Now we've looked at this idea of the rate of reaction, how fast a reaction occurs, and seen that it can be affected by a range of things. So concentration, temperature, the pressure for gases, surface area of solid reactants, and the presence or absence of a catalyst. All of these things are going to affect the rate of a reaction. But we've said that at equilibrium we have a forward reaction and a reverse reaction, each of which has its own rate. Once we've established equilibrium, those rates are equal, but they're not zero. And so then it kind of begs the question, saying, all right, well, how do these factors affect both of the rates? Is it just one being affected, or is the other one being affected? Okay, but the idea is that in reversible reactions, all of these factors still affect them, but they will affect the rate of both forward and reverse reactions. Okay, so the idea being, all right, well, that these are still factors that come into play. We just need to then consider, right, what's it doing to the forward? What's it doing to the reverse reaction? How does that then cause a new equilibrium to be established, perhaps? Okay, what we're going to see is that in the next kind of section, that we're going to look at the factors that affect equilibrium, and we're going to discuss it in terms of effect on these rates of reaction, because shifting an equilibrium is not only possible, but necessary and important for us to understand. Okay, but so the rates of both reactions are still affected by these things. And then we introduce a concept we call equilibrium position, saying, all right, well, at equilibrium, it's easy for us to assume that, well, does that mean that then we have half of everything, like it's half each, half reactants, half products? But the reality is that lots of equilibria don't exist in that way. That at some point, once we establish equilibrium, we have a certain amount of reactants versus products. So equilibrium is the position, is the term we use to describe, well, where's the relative amount of reactants and products for this equilibrium? With reference to the equation, is it predominantly on the left side, the reactant side? Is it predominantly on the product side? Is it kind of in between? If we look at these reactions here, or these two kind of hypotheticals, this first one lies mostly on the right-hand side because it's 80% B and only 20% A. The second example, though, it's predominantly on the left side because it's 80% A versus 20% B. And we can sometimes use the arrows, the relative length of the forward and reverse arrows, to try and visually represent that, saying, all right, well, yes, it's at equilibrium, but most of the substances are on this side or that side. Okay, so we talk about that as the equilibrium position. Again, this is something we're going to unpack further. We can actually calculate how much is present at the equilibrium position once we kind of get a little further down the road. Okay, but one thing to understand is it's not necessarily a 50-50 mixture. Now, it may be, but it's not typically. Okay, and what we can also see is that the equilibrium position is independent of whether we start with the reactants or we start with the product. So you can see with the graphs here, for this reaction between hydrogen and iodine as elements to form hydrogen iodide, if we just start with hydrogen iodide, the grey line, then we will re-establish equilibrium and we have relative amounts of product and reactants. But if we just start with our reactants, the purple line, then we eventually end up establishing equilibrium again, but the relative amounts of each thing is still the same. So it doesn't matter whether we're starting from the forward reaction or starting from the reverse reaction. Eventually we roll back down to the middle, which is where equilibrium is established. Okay, so it just goes to show that equilibrium position is independent of which point you start from. It always comes back to that middle. Okay, and the concentration that we would calculate at those points will be the same regardless of which one we start with. Okay, so we introduced the concepts, reminded ourselves of collision theory, this idea that you need kinetic energy, you need the correct orientation for a successful collision, a successful reaction. That the activation energy is the threshold to get over, that reversible reactions tend to have a small activation energy in both directions and similar activation energies, so that it's easy, relatively simple or equally kind of difficult to go forwards or backwards. Okay, that the rate of reaction is affected, these factors affect both the forward and reverse reactions, and then equilibrium position is the relative amounts of all the substances present at equilibrium, and whether it lies to the left-hand side or the right-hand side. All right, thanks very much for watching. Bye for now.